All right, we're starting our new unit today, and our new unit is on magnetism. Before we go any further with it, I want you to remember one thing, and one very important thing. Although a lot of the things that we're going to do in this unit have a lot of similarities with electricity, and there are connections with electricity, and there are ways, lots of places that we can get confused with electricity, this is not electricity. Magnetism is a different topic than electricity. In electricity, we talk about fields. We talk about fields in magnetism as well. In electricity, we talk about laws and attraction and repulsion. We talk about that in magnetism as well. And that's reason why it's easy to become confused between the two. But in the end, electricity deals with charges, positives and negatives. Magnetism deals with poles, north poles and south poles. And a positive charge is not the same thing as a north pole. And a negative charge isn't the same thing as a south pole, even though there's a lot of similarities, and they can be in many ways very analogous to each other. All right, with that out of the way, let's define a term. A domain, a magnetic domain. This is such a great definition that probably nobody, when they first read it, is going to understand really what a magnetic domain is. It's a tiny little region inside a ferromagnetic material that's represented by an arrow. Do you have a perfect understanding of a domain now? Really doesn't mean anything to us, right? Because what's a ferromagnetic material? We got a tiny little region inside a ferromagnetic material. It doesn't make any sense if we don't know what a ferromagnetic material is. A ferromagnetic material is a material that can be magnetized. It's not magnetized right now, but it can be magnetized. For example, the leg of your desk isn't a magnet right now. It's just a piece of steel. But that piece of steel can become magnetized. If I bring another magnet nearby and hold it there for long enough, then that leg of the desk can become a magnet, at least a temporary magnet. Steel is a ferromagnetic material. Iron is another ferromagnetic material that's not necessarily a magnet, but has the ability to become a magnet. It has these tiny little domains, these tiny little regions inside it that can become aligned and therefore become a ferromagnetic material or become a magnet. What's the chemical symbol, by the way, for iron, just out of curiosity? Fe? What does that mean? What's it come from? I think it's Latin, actually. I think it's Latin. Ferrous? Ferromagnetic, that's where the whole ferromagnetic comes from, right? Is ferrous, Latin for something like iron? Something like that? I don't know what the base word means, but it means the same thing, obviously, right? Iron and ferromagnetic come from the same base word, and it's not a coincidence that they come from the same base word. Iron is a really, really common ferromagnetic material. Okay, so it's a tiny little region inside a ferromagnetic material that can become magnetized, and it's represented by arrows. Now, clearly, if we have a real ferromagnetic material, a piece of steel or a piece of iron or some other ferromagnetic material, we don't literally have these arrows inside it. If we look in a microscope, we're not going to see these little arrows floating around inside it. Rather, what we see is atoms and electrons spinning in certain ways, and commonalities between electrons spinning in certain ways. If we group together electrons that are spinning in certain ways, we get these little regions. We represent these little regions by arrows. We can't draw the spins of electrons, so what we do is draw arrows that represent these commonalities in these spins. These arrows are what we use to represent these domains, these common regions of electron spins, and so on. Normally in a ferromagnetic material, these domains or these arrows point in more or less random directions. But we can get them to point in the same direction, and when we do get them to point in the same direction, then we don't have a ferromagnetic material anymore, we have a magnetic material. We have a magnet. So if we can take these arrows that we see in this diagram here and get them pointing in the same direction, at least more or less in the same direction, then we've changed it from a ferromagnetic material, just a regular piece of steel that is the leg of your desk, into a magnet. Now, how do we do that? How do we cause these domains to become aligned, to point in a particular direction? There's a couple ways. One way, pretty simple, bring another magnet nearby. Bring something that already has its domains aligned nearby. That will cause the domains in this non-magnetized ferromagnetic material to start pointing in the same direction. We'll start aligning them. Then it becomes a magnet. So bring another magnet nearby, you can magnetize something. The other way to do it, and we'll talk a lot more about this next week, but the other way to do it is to wrap a wire around it. Wrap a bunch of loops of wire around it and attach that wire to a battery. Apply an electric current through that wire. An electric current, you're going to learn next week, generates a magnetic field. That magnetic field can cause the domains inside this non-magnetized ferromagnetic material to start pointing in the same direction. This thing becomes a magnet now. It's an electromagnet. You see these at junkyards on TV, right? Trying to pick up cars at the junkyard where they bring this thing over, this kind of crane over, but they don't scoop it up. They just bring this thing over and touch the car. It sucks up the car. Then they bring it over here and then they drop it. It's an electromagnet. It's a really, really strong electromagnet with a lot of loops of wire around it. Flip a switch, run the current through it, magnetizes the piece of steel that's in the middle. Flip the switch off, current turns off, demagnetizes the piece of steel that's in the middle and the car drops. Does that make sense? Now, let me redraw this as a magnet now. Let's assume that we've already magnetized this ferromagnetic material. These domains that you see pointing in the same direction now, which give us a magnet, produce a certain polarity. This magnet will have a polarity that looks like that, a south pole at one end and a north pole that looks that's at the other end. The magnetic domains will point from south to north. That's arbitrary. We define it that way. We just say the domains point from south to north. But in the end, we've got to define it one way or the other, so it's as good this way as the other way. Domains point from south to north. What do you think is going to happen if I take that magnet and, for whatever reason, I break it in half or I cut it in half? Now I've got two magnets, right? I've got a south magnet and I've got a north magnet, right? We just said magnetic domains point from south to north. If we define them as pointing from south to north, then there always must be a south pole where they're coming from and a north pole where they're going to. So if you cut that magnet in half, you're not going to get a south magnet and a north magnet. You're going to get a south and a north magnet, a south and a north magnet. You're going to get two magnets, right? Does that make sense? There's one of the big differences with electricity, right? You can have a single charge, a positive or a negative, or you can have both. With magnetism, you can only have two poles. You can only have a north and a south. You can't have one or the other. All right? There are, just like in electricity, three laws of magnetism. The first law of magnetism, not unlike the first law of electricity. Like poles attract. Repel. Like poles repel. North repels north, south repels south. It's a lot like positive repels positive and negative repels negative. It's for a different reason. We're dealing with magnetism as opposed to electricity. It's magnetic fields as opposed to electric fields that cause that. But in the end, the effect is the same. Two things that are the same repel each other. Two things that are different attract each other. What do you think the second one's going to be? Even though you've never seen this before, you guys are so smart that you're going to figure out the next one. Opposite poles attract. Unlike poles attract. North attracts south, south attracts north. The third one, this one's a little bit tougher, but you can at least get part of it, I think. was the third law of electricity? Charged objects attract neutral objects. Remember, we're not talking about charges, so don't mention the word charge. Don't mention the word neutral. Pete? Good. Okay. Magnets will attract non-magnetized ferromagnetic materials. I asked this one this morning, and somebody said, magnets will attract non-magnets. Well, they're on the right track. Sometimes that happens, right? If you take a magnet and bring it nearby the leg of your desk, which is a non-magnet, it'll attract it. But if you bring that magnet nearby the piece of paper that's sitting on top of your desk, the piece of paper won't be attracted to it, right? That non-magnetized object, in order to be attracted, has to be ferromagnetic. So magnets, or either a north or a south pole, attract non-magnetized ferromagnetic materials. And why does this happen? For a similar reason as charged objects attract neutral objects. Remember we said that there's an induced separation, temporary separation of charge? Here we've got induction again, but it's not electrical induction. We're inducing a temporary alignment of domains. So the non-magnet, the ferromagnetic material, we temporarily induce these domains to point in the same direction. Bring the other magnet away from it, and they go back more or less to the way they were. So it's only temporary. But it lasts as long as it needs to. There's the other one that I couldn't resist. Get it? Magnet, non-magnetized ferromagnetic material. Yeah. All right, we'll move on. All right, we've talked about gravitational fields, the fields caused by masses. We've talked about electric fields, the fields caused by charges. Now we're going to talk about magnetic fields, the fields caused by magnets. Good. A field is a line of influence that surrounds something, surrounds a mass, surrounds a charge, or that surrounds a magnet. Magnetic fields are vector fields, just like electric fields are, and just like gravitational fields are. So they have a particular direction associated with them. We're going to learn the direction of that magnetic field today, and we're going to learn the shape of that magnetic field today. In order to do that, we're going to do a little activity here. Okay? I'm going to give you a piece of paper in a second with 3 pictures that look a lot like this. Each of those pictures has a picture of a magnet, and it has a bunch of little stars around it. What I want you to do is take a magnet, or some of the diagrams have 2 magnets, take a compass, and I want you to place the compass in every place where you see a star around the magnet. So for instance, right here, I see a star right above the magnet. I want to put my compass right above the magnet, and I want to draw a little arrow on that star indicating which way the compass points. So if the compass points up, draw a short little arrow pointing up. If it points down and to the left, draw a short little arrow pointing down and to the left. You do that for all 3 diagrams. Once you've done that, we will hopefully start seeing patterns. Then we're going to go back to kindergarten, and we're going to start joining the dots. And we'll see what kind of picture we get when we join the dots. All right? All right, now that pretty much everyone's finished, let's take a look at what we should have seen. If we drew arrows representing the direction that the compass was pointing at all of these different stars, then we would have got something that looked like this. If yours didn't look exactly like this, that's okay. And by exactly, I mean not at all like. So if it didn't look at all like this, that's okay. But in the end, this is what we should have gotten. Okay? The compasses that we're using weren't great, and we're doing it on a desk that has steel legs that are all around it. So there's lots of outside influences. There could have been somebody next to you, a group next to you with some magnets that could have been influencing it. Maybe the second magnet that you had was too close to it and it was influencing your compass. Whatever, it's not the end of the world. If you didn't get something that looks like this, it's okay, but this is what you should have got. That means you were drawing the wrong direction of the arrow then. You're looking at the wrong end of the compass needle if you get the exact opposite. Now I wanted you to draw whichever end pointed towards silver. Okay. Okay. What did you say was, did you say this was red and this was silver? Okay, the North Pole would have normally been the red side of the compass, or the magnet. So you just had your magnet turned around, no big deal. If we join these lines together, then we get something that looks like this. Now this may not look familiar to you right now, but if I draw one other type of field that you've already seen before, an electric field that surrounds a positive and negative, it might start looking familiar. You guys remember the electric field surrounding a positive and negative? Just wrote a test on that here yesterday, right? Those look a lot alike. They're two different fields. One's magnetic, one's electric, but the shape of the field is virtually identical. If we have a north pole and a south pole, it's like having a positive and a negative charge. The field will look the same, except that it's a magnetic field given by the symbol B, as opposed to an electric field given by the symbol E. Let's try the next one. Here we should have got something that looks like this. I'm not going to draw all these in because it's going to take me forever if I do that for all the diagrams here. Something that looks like this. We start joining the lines together, and it should look something like this. Well, if we think back to electric fields again, that might look somewhat familiar as well. If we take a positive charge and a negative charge, and then another positive, and then another negative, and we draw the field lines surrounding those, it's going to look something like this. Field lines go from positive to negative, right? But then, of course, we have to join these two together as well, so it kind of goes like this, from positive to negative. Does that look like the field above? So the magnetic field shape looks like the electric field shape if we had 4 charges, 2 positives and 2 negatives. It's not the same field. It's magnetic, not electric, but it looks the same. The symbol is a capital B, yes. Yes. Don't panic about that yet. We'll deal with that more later on. But it's kind of an odd unit, I know, or an odd symbol for magnetic field, but it is what it is. Okay, one more. Here we have field lines going like this. Okay, and then a bunch of other ones as well. If we join those lines together, or join those points together, we're going to find that it looks something like this. Recognize that? Now, if we draw 4 charges again, a positive and a negative, I should say, and a positive, and then we got another positive and then another negative, and we draw the field lines in between the positives and the negatives, it's going to look like this. But if we draw the field line between the positive and the positive, they push each other away because they repel each other. Looks a lot the same again. The magnetic field shape is the same as the electric field shape, but just remember that it's a magnetic field, not an electric field. Make sense? How many people got something that more or less on the 3 diagrams that look like this? More or less, except the exact opposite because you had your magnets flipped around, but that's not a big deal. Okay? If you had to flip your magnets around, you would have got the same thing, right? All right, I want to define magnetic field in 2 ways. Magnetic field direction, that is, in 2 ways, and then we'll wrap it up for the day. We know that it's a line of influence that surrounds a magnet. Just like an electric field is a line of influence that surrounds a charge, and a gravitational field is a line of influence that surrounds a mass. We know that it's a vector field. We represented it by arrows, so it's got to be a vector field. There's got to be a direction. How do we define the direction? Well, number one, it's the way that a compass needle will point when placed in the field. That's what we just did, right? We put a compass in the field, then we looked at which way that compass needle points. The second way we define the direction of a magnetic field, and you can see that from the diagrams that we drew, is from north to south. Magnetic field goes away from the North Pole towards the South Pole, just like the electric field goes away from the positive and toward the negative. Now this creates what seems to be a little bit of a conflict. But we can resolve it if you even kind of spot the conflict right now. Let's draw a picture of the Earth for a second. The Earth is this big ball of rock and dirt and molten magma churning around inside. This molten magma churning around inside the Earth generates a magnetic field. This magnetic field looks like, a lot like, the magnetic field surrounding a bar magnet. Let's draw that little imaginary bar magnet inside the Earth. I'm not going to label the poles right now, but I will draw the magnetic field that surrounds it. Okay, it looks like the magnetic field surrounding it, just a plain, simple bar magnet. This is the equator right here. If I'm standing at the equator right here, and I take a compass out of my pocket, which way will that compass point? Remember, this is Canada, and this is Antarctica. This is where Santa Claus lives, and this is where the penguins live. Which way will the compass point when I'm standing at the equator? Points toward Santa Claus, right? Toward Canada, northern Canada, or where Santa Claus lives. So let's draw that in. The magnetic field lines all should point this way. What are the two ways that we just defined direction of magnetic field as? The way that a compass points when placed in the field, and from north to south, right? From north to south. So what does that tell us? It tells us that Santa Claus doesn't live, brace yourselves here, Santa Claus does not live in the North Pole. Santa Claus lives in the South Pole. What? Doesn't make any sense. Geographically, it's as we always have thought of it. The North Pole is Canada and the South Pole is the equator. But magnetically, that's not the case. Magnetically, it's the exact opposite. Magnetic North Pole, strictly speaking, is in Antarctica, and magnetic South Pole is northern, or I was going to say is in northern Canada. It's not really. It's very, very near northern Canada. It's actually just outside of the Canadian boundaries. But we might as well say that it's in northern Canada. Magnetic south is where Santa Claus lives. Magnetic north is where the penguins live. Now, if you happen to find yourself lost, you got a compass. Okay, don't change the way you navigate. Okay, when you're looking in your car and it says, you know, a little digital display above the dash, it says that you're going north. What it really means is you're going geographic north, magnetic south. It doesn't change anything. Okay, it's just a name. It's just a name that, as long as we understand and all use the same frame of reference, doesn't really matter. I don't know. I don't know. When we navigate, we think of Canada as being the North Pole, right? Well, it's not. It's the South Pole. But if everybody's using the same system, it doesn't really matter. If I said to Adele, if Adele was getting in trouble again, and I said, no, just kidding, Adele. If Adele got in trouble and had to go to Mrs. Staffichuk's office, and I said, Adele, go to Mrs. Staffichuk's office now. And Adele wasn't sure where well, Adele thought she knew where Mrs. Staffichuk's office was, but she went to the wrong place because it wasn't really Mrs. Staffichuk's office. She was confused about that. But if Mrs. Staffichuk was also confused where her office was and was sitting in the wrong place, then it doesn't really matter because you end up going to the right place, right? If everybody says northern Canada is north, then it doesn't really matter if it's right, as long as we're all using the same reference when we're navigating. Does that make sense? Technically, it's magnetic south. But if we all call it north when we're navigating, then it might as well be north. It doesn't really matter what it really is if we're all calling it the same thing, even if we're all calling it exactly the opposite of what it's really supposed to be. Don't forget, though, it is truly geographic north. It's not magnetic. Sorry, it's not geographic south. It's magnetic south, but it's still geographic north. Just that compasses measure magnetic poles instead of geographic poles. All right, that's it for today.